Okay, another method, KNN or K nearest neighbors, I will call it KNN from now on, is a predictive model or method, better to say, that can cope with both regression and classification problems. So it's quite versatile. Okay, it's ambidextrous. It's a straightforward method based on similarity of a new observation with the historical ones. So the reason that I have added KNN to our stack of algorithms in this module is because, well, it's quite simple and straightforward and intuitive. It's ambidextrous. It can deal with both regression and classification problem. And it's one of the most famous algorithms in general. So there is not that much of why behind predictive methods. The methods are efforts to achieve better performances. KNN is different from other methods because it does not have any parameter. Okay? And basically it is called, so for sake of fun, it is called lazy learner. It's a lazy learner. It does not learn in the classical way that we have learned from the training data set. And it does some other tricks. So actually it does not tell you how the predictors are related to the target in the classical way that we have seen in decision trees, let's say. And it is interesting from this point of view. So through an example, we will see that how it works actually, and things would be more clear. Let's assume that this is a feature space. This is predictor 2. This is predictor 1. And we have two sorts of outcome. So we have some reds and we have some blues. And suddenly there is this so maybe this is not a good color, let me change it. And suddenly there is this new observation. And this observation and this observation. So we want the algorithm to predict the outcome of these observations, the target value of these observations. Okay, so the first observation, this is predictor 1, and this is its predictor 2. Okay, all the methods that we have learned so far, they try to establish a relation between predictor 1, predictor 2 from one side and the target variable from the other side. But KNN doesn't try to do so. And this is its trick. Okay. It says that, okay, tell me the K. I am K nearest neighbor. So tell me that what are the K nearest neighbors of the new observation? Let's say keep K equal to 3. It says that, okay, this is the first one, this is the first one, and this is the first one. These are the 3 closest neighbors. All of them are, the output are red, so my prediction for this one would be red. What about this one? It says that all the closest neighbors, 3 closest neighbors, because you told me to check the 3 closest neighbors, all of them are blue, so my prediction about this observation is blue. But what about this one? You're saying that this is one of them, and this is another one. So again, considering k equal to 3, I have found the 3 closest neighbors to this new point, and 2 of them are red. So they are majority. My guess is the output of this one is also red. The target is red. So KNN is as simple as this. It does not learn in the classical way from the training data set, but it maps every new observation to the training set, considers a neighborhood, and the neighborhood, the number of items that it should consider, is a hyperparameter. So we have to tell the algorithm what is this value, and it will tell you whether this the outcome would be this and that based on the neighbors. So there is this big assumption that you are like your neighbors. Okay? A new observation is like its neighbors. So then the outcome must be similar, must be something similar. So in this classification problem, the output is calculated by the mode of that neighborhood. If it is a regression problem, then the output would be calculated by mean of the neighborhood. So it's quite simple. Let me see whether I can move this one without moving the axis. I cannot, so leave it here. So it's that simple. It's quite simple, I guess. And this is why I like it, and it's quite efficient. So there are hyperparameters that you have to tune at the end. One of them is how we measure closeness, how we measure the neighborhood, the similarity, because the neighborhood is based on similarity. So there are different ways to measure similarity. One of them is Euclidean. The other one is Manhattan. And we have Manning and more and more. Okay, this is one hyperparameter. The other one is the number of neighbors. Do you want to consider only one neighbor? 2 neighbors? 10 neighbors? We don't know. So because these are hyperparameters and we need to tune the hyperparameters. Through trial and error. Good. So when to use KNN? Well, it's always a good choice. Except it might not be a very good choice when we have too many predictors, especially comparing to the number of observations. In any case, we should judge the method based on its performance on the test data, and we should not rule out trying a method. Okay. And there's very little cost in trying a method. It's just a little bit of computation and time, and we can get the result. So we shouldn't rule out KNN for any problem. But in general, well, we have too many predictors for some mathematical reasons. KNN would not perform very well probably. But it's always a good idea to use it and to see its performance. Maybe we should give a chance to KNN always. Okay? So yeah, that was about KNN. And let's go to talk about the next method.